Okay, so are there any questions from the previous lecture? There is anything that you want to clarify? Okay, so then I think we should move on. So we had few questions last time, right? When we towards the end of the lecture, is the set of reals countable? Is the power set of natural numbers countable, and so on? Is the set of rational irrationals countable? These questions. So these we will try to answer in this lecture. Okay. So just to quickly recap, we looked at sets which can be finite sets.
Ma'am, could you talk a bit more loudly? I'm not able to hear.
Oh, okay. Yeah, is this fine now?
Yeah, yes, ma'am. Now it is.
Okay, okay. Okay, great. So yeah, if you cannot hear properly or if you want me to talk a bit loudly, please tell, okay, because I may not be able to realize. Once you say it, it will be better for me. Okay, so we looked at sets, and sets can be either finite or infinite. Right? When you look at finite sets, naturally these sets are countable because you can assign a natural number to each element in the set, and you can create a bijection between the given set and the set of natural numbers. And there are also infinite sets. We looked at Z, Q, and so on. There, if you think a bit more, you were able to come up with a bijection between the given infinite set and the set of natural numbers. So you say a set is countable. More precisely, you say that the infinite set is countable because finite sets are always countable. Countable if, let's say, a set S is countable if there exists a bijection F from S to N. So this way we were able to show that the set of integers, the set of rationals, these are all countable. So next natural question to ask is what we had posed last time. Is the set of real numbers countable? Right? So that is what we want to try and answer. The question is reals countable? So did any of you get to think about it? Yeah, what do you think the answer to this question is? Those who have already seen the proof, I'm not sure. You would want to say because you know the truth, right? So somebody who has not seen these things before. Given that rationals are countable, so then rationals, if you think about it, between any two rational numbers are infinitely many rational numbers. But somehow we were able to nicely come up with this diagonal sort of construction, right? Where we could list or enumerate the rational numbers in a certain fashion so that every rational number was in this list at some point. So do you think you could do the same thing with reals? Okay. So maybe you haven't guessed or you all know the answer to this. So the answer to this is no. The set of real numbers is not countable. So what do we mean by that? You say a set S is uncountable if it is not countable. So what do we mean by that? There cannot exist a bijection between this set and the set of natural numbers. Okay? On first looks, it seems very strange, right? How does one prove that there cannot exist any function that is a bijection between the given set and the set of natural numbers? If you look at this for the first time, if you're seeing this for the first time, it might seem very strong. So this, the fact that uncountable sets exist and also reals is uncountable is a famous argument due to Cantor. It's called Cantor's diagonalization argument. So that's what we want to say. Okay, so suppose for the purpose of completion, let us assume that the set of reals is countable. So let R be countable. So one thing that we observed last time, we stated last time that we did not prove, is that the subset or that any subset of a countable set is countable. Right? So let us use it But after we prove this, we will prove that statement also. But for now, let's just use that fact. So I will write it as a fact, but we will prove it towards the end of the class. Subset of any countable set is countable. So when we say subset of any countable set is countable, suppose there is a countable set and you look at a finite subset of it, it naturally is countable. So the interesting part of the statement is, if you look at any infinite subset of a countable set, that is also countable. Right? It might seem natural, but how to construct the bijection, that is the question. But let us just believe this fact for the moment and try to prove that reals are uncountable. But we are beginning with the assumption that the set of reals is countable. And any subset of reals is also countable from this fact. Right? Any subset of R is countable. Or in particular, you can pick your favorite subset and work with it. Right? So let's pick this interval 0, 1. Right? This is a subset of R. This set is countable. So we are beginning with the assumption that R is countable. Now we have that the interval 0, 1 is countable. So if it is countable, then what can you say? You can in some sense list or enumerate all possible real numbers in this interval, right? So there is an order in which you can write down all the real numbers in this interval, and you can assign natural numbers to these. So let us just do that. From definition, R1, R2, R3, R4, these are all real numbers. So R1 is 0 point. There are some decimal digits after this, right? So let's call this D11, D12, D12. You can hear, right? Was there a question? Okay. So these are the decimal digits after the decimal points in R1. Similarly, R2 is D0 point, D21, D22, D23, D24. I just write down everything so that it's easy for us. Similarly, all the reals in the interval 0, 1 can be listed this way. Right? So now, every real number should appear somewhere in this list, right? If it is in the interval 0, 1. So that is the first observation. Every real number in 0, 1 appears somewhere in the above. So, in order to show that it is uncountable, because you know the truth, and I'm telling you that this set is not countable, what you must try to do is somehow construct a real number that could not potentially lie in this list. Right? In this listing, somewhere it should never appear anywhere. That is the kind of real number that we want to construct. So what could that real number be? Just by looking at these rows that I've written here, can someone try to come up with a real number such that it is unlikely that this real number is in the table? Let's see. So I will give you a hint and then we will see if you can try to figure it out. Given the name campus data, it has something to do with the diagram. So let's look at this real number. D22, D33, D44, and so on. This should also appear somewhere in this list, right? Let's call this R. Now, can I somehow tweak this real number R to get another real number which might not lie in this list? Is this possible? Maybe you can try, right? You could try to do it. So if you look at the rkth row in this list, right, it has 0 point, dk1, dk2 for any dk3, so on to If you look at the kth index from here, it will be DKK. Right? So now we are given this hint also. This is hint 2. Right? Hint 1 was the diagonal and hint 2 is this. Now can you construct a real number R theta 0. So these decimal digits you have to construct. So that for any k, R tilde can never be equal to RK. You have to construct find R tilde such that R tilde is not equal to RK for any k. Can someone try to come up with such a real number? Is the argument clear so far, or are there any questions? Yeah, please stop if there are any questions. It's like very, very important.
Okay, the digit can be 9 minus DKK.
It can be anything but DK, right? Is that clear to everybody? So is the flow of the argument clear? Like what this real number R tilde is, we have not defined, but at least what we are going towards. Is that clear? Okay. I hope it's clear because you have not posted any questions on chat. Okay. So then what we have to do, just as someone suggested, that we know that for every k, if you look at the real number in the RK row, the corresponding kth digit is DKK. So if I take that to be DKK plus 1, let's say, then this particular diagonal, right, the one here, this cannot appear here, right? Because in this number it is DKK, whereas in R tilde it is DKK plus 1. So let's just write down R tilde for 1. This is 0. I'll just put D11 plus 1. This is not exactly required. It can be D11 minus 1, D11 plus 9, anything that is different. And so you construct a real number such that you look at the diagonal here and you increase every DII to DII plus 1. If it is 9, you get back to 0 or 1. So let's say this real number is constructed modulo 9. Okay, because so each DII is in 0. Okay, so look at this diagonal and look at R tilde. Suppose R tilde appeared somewhere in the list. Right? Let's just try to write this. Suppose R tilde is equal to RK for some k. Right? So which means that this right now is your R tilde. Right? So what can you say? Right? Because the way R tilde was constructed, right, in the kth position, you will get that it is DKK and DKK plus 1, right, which is not possible. So for any RK, you know that the kth digit is DKK, but you carefully constructed R tilde so that this kth index is DKK plus 1. Right? So it cannot be two things. Is this clear? And the kth index is both DKK and DKK plus 1. So this is a contradiction. So what is the only thing we assumed here? The only thing we assumed here was that every real number in 0, 1 appears somewhere in the above table. So R tilde does not appear in the above list. And R tilde is a valid real number, right? So this is in the interval 0, 1. Which means that the set of reals is not countable. So you could not have enumerated all the real numbers in this fashion. Are there any questions about this argument? So this argument is famously called the diagonalization argument, because you use the diagonal to construct a new real number that cannot appear anywhere in the list. No questions? Have you all seen this argument earlier in real analysis? Any surprise? Or are you like so shocked that you don't know the question?
Ma'am, we didn't do it in real analysis, but I've seen the argument before.
Okay, was
And
this
I-
done in TOC maybe? Whatever,
Oh, we
theory,
haven't had
whatever.
TOC yet.
Oh, okay. So at least few of you might be seeing this for the first time, right? At least one of you.
Ma'am,
Huh.
can we prove the uncountability of R without using decimal representations?
Okay. Yeah, probably something similar to what he had hinted the other time, that you can write reals as Q union set of irrationals. And then if you can prove the set of irrationals is uncountable, you know that if R is countable, then this has to be countable, right? So you can use that. Or is there some other technique that is in your mind you want to use?
No, ma'am.
To prove
I was asking question.
Sorry, I could not hear the last sentence.
No, ma'am. What were you asking?
No. So is there any particular proof that you have in mind and you want to know if that works, or is this a general?
No. I don't have anything in my mind.
Okay. So one way to think about it is write reals as the union of two sets and see if both are. If both are countable, then reals must be countable, right? But this we haven't proven yet. That countable union of countable sets is countable. We will show that today. So at the end of the lecture, one thing you could do is to show that reals is if reals were countable, then these two sets have to be countable, right? But you can try to show that set of irrationals are uncountable. But at least most of the arguments that show that a given set is uncountable is via Cantor's diagonalization. In fact, not just showing that reals is uncountable, right? Showing that there are problems that cannot be solved by computers. That itself follows Cantor's diagonalization. We will try to do it if we have time. Otherwise, in the theory of computation course, you'll see that. But there are problems that you can, if you enumerate all the problems in the universe, right, there will be some problem that is not released. So one way to think about it is, in the end, how does a machine read whatever problem you want to solve? Everything is in byte. Okay? At the end of it, no matter what programs you write in C, C++, Java, whatever high-end languages you use, in the end, everything will be encoded in zeros and ones. So what we have is as a binary string. Right? So every problem you can encode as a binary string. And what you want to ask is, look at the set of all infinite length binary strings. Is this set countable? If the set is not, then there is definitely one string that is not in this list, and that string somehow encodes a problem, right, which cannot be solved by computer in a certain number of steps. So this is a very fundamental result. It's beyond understanding countable sets. It has applications to understanding whether all problems can be solved by computers. So you will see this, see the halting problem. Yeah, if there is time, we can try to do that. But for that, we have to develop machinery of Turing machines. So at the moment, at least this argument should be clear that reals is not countable. So we had here, if you looked at the picture from the last lecture.
Ma'am, the reason I asked the question about the decimal representations is because like we haven't proved that all real numbers can be represented as decimal.
Yeah, that is true. Yeah, so that I assume. Yeah, that I just assume. That
Okay.
Has a decimal representation. Yeah, that is true. Yeah, it might be slightly difficult to prove everything about real numbers in this course, but that is something else. So this these things are all countable. And reals. Okay, so now that you have seen this proof and you did not raise any questions, so I'm assuming that you understand the proof. Now let's go to the other question that we saw the other day, which is about power set of natural numbers. So if you remember, so this question is done. Next, I want to look at this question. where you want to look at power sets of a natural, the set of natural numbers. So in general, you can also look at power sets of a set. So if A is a set, then P of A is the set of all subsets. A. So if A is finite, let's say the cardinality of A is n, then what can you say about the cardinality of P of A?
2 raised to n.
2 raised to n, right? So for any set A, if you look at the cardinality of the set A with the power set of A, the power set has strictly larger cardinality than the set itself, right? Assuming a non-empty set A. Right? So now what can we say about infinite sets? That is the question. So let A be an infinite set. For our purpose, let us think about it as n. We want to look at the power set of natural numbers. So this has all possible subsets of natural numbers, including infinite subsets. So somebody had asked last time. It has the null set, it has the set of natural numbers, all singletons, all possible subsets of all possible sizes, including infinite sets. Yeah, so one of them had suggested that if P of n is countable, you have to associate a natural number to each of them. So you look at the concatenation of all the elements in the set and consider that as a natural number, then that will be a bijection. But this will work if only the finite sets are included, finite subsets. But now there are infinite subsets. So what is the natural number you can associate with the set of natural numbers itself is not clear. So now I will give you the answer that this set is not countable.
Ma'am.
Huh.
Yesterday I was the one who said that you could
Okay.
concat.
Mhm.
I sort of thought about it, and the concatenation idea can also be used to show that this is actually not this is uncountable. Like we can only use we can use that only. So instead of taking like concatenating them just like that, we'll just add a decimal point before all of them. So we can show that this will actually be we can put this set in
Reals?
bijection with reals exactly.
Yeah, because you have seen now that reals are uncountable, then PFN is also uncountable. That is right.
Yeah.
So it is clear, right? Whatever he's saying. So put a decimal point before it, write it as 0 point, the sequence of all the, so order the elements in the set in some order and then put them there. Then you will get real numbers. This will be a subset of real numbers. So using the same argument as before, you can show the PFN is uncountable. That is it. But we will see a different proof. Actually, I want to demonstrate diagonalization again. This as another example, so that you get very familiar with that. So one question that I expected someone to ask is, okay, we know that reals are uncountable, right? So what does this say about the comparison between the cardinality of reals and the cardinality of naturals? So we know that, so n, if you look at it, this is you know that cardinality of n, we denoted it by some constant that is used to denote. Now, what can you say about the cardinality of reals versus the cardinality of naturals?
It's larger.
So the cardinality of reals is strictly greater than the cardinality of natural numbers. Why is that? If it has the same cardinality, then it would have been countable. That is how we define countable. So in other words, you can say a set is countable if it has the same cardinality as the set of natural numbers. So anything larger is uncountable. So now in math, people use this symbol C to denote the cardinality of real numbers. It's C. So some books might use that this set is uncountable and has cardinality C, which means that this set has the same cardinality as the set of reals. So similar to what I think Rajdeep had pointed out, P of n has the same cardinality of reals because he was able to come up with a bijection, right, to this and the subset. Okay, but these things we have to show what can we say about a subset of reals and reals itself, an infinite subset of reals. Does it have the same cardinality as the set of reals? So these things we have to think about. We will slowly answer them. But just to ensure that you see if you see this notation somewhere in the textbook, you have to correlate this with the subset of with the cardinality.
So, ma'am, the thing you stated in the last class that if from A to B we have a surjective map and which is not injective, then even for infinite sets, can we say that cardinality A greater than cardinality B?
Okay. So what is the question?
So
there?
if we find a map from A to B, a surjective map which is
Okay.
not injective,
Okay.
so many to one maybe. So then even for infinite sets, can we say that cardinality A greater than cardinality B?
Yeah, exactly. So the other way around also you can think, right? So if there is an injective map, we know that cardinality of, I'm just rephrasing what you said. So if there is an injective map, so the sets are all infinite. So if the sets are finite, there might not be that much trouble. If there is an injective map, can you also construct another subjective map? Right? Suppose you were able to do it. I give you an injective map between two sets A and B, and you give me a subjective map between two sets, between the same two sets, right? From B to A in the other direction. Then you can say that the cardinality of these two sets are equal. So from an injective map, you can construct a subjective map. We will see that towards the end of this class or in the beginning of the next class. This theorem is called Cantor-Schroeder-Bernstein theorem. It's very natural, right? For infinite sets, we don't know how they behave. Just because there is an injective function, we don't know if there can be a subjective function. Can we use these two functions to get a bijective function and other things? For example, whatever question he asked, if you understand, it relates exactly to this approach that someone had suggested. This one, right? To show that the Cartesian product of two sets are countable, you can just look at these two elements, m, and map it to a natural number 2 to the n times 3 to the n. This map is injective. But this does not immediately say that n cross n is countable, because for it to be countable, you have to actually demonstrate a bijection. But you are only demonstrating an injection. So is this itself sufficient to show countability of the Cartesian product? That is the same question as he's asking. We will see that in the end of this lecture, or maybe next lecture. Yeah, I'm not sure how much time we have. Does that answer? Or maybe I went really fast.
Yes, ma'am.
Okay, yeah. So this theorem, whatever he is asking, the answer to that is given by Cantor-Schroeder-Bernstein theorem. We'll see that next. Okay, so I just wanted to ensure that whenever you see this number, you need to associate it to the cardinality of natural numbers and this to the cardinality of reals. So one question that you might ask is there any set in between, right, between these two sets? Is there any set that has cardinality strictly larger than F0 and strictly less than C? Right? So this is called the continuum hypothesis. This is just a fun fact. So if you want, you can try to Google about it. This is a hypothesis that Cantor proposed. He asked this question, can we find? So we now know that there are two sets of different cardinalities. One with smaller cardinality, one with a larger cardinality. Can we find some set in between these two sets? So yeah, if you want, but this is more like a fun fact. We may not do much of this. I think there is a UU. Yeah, I'm not entirely sure about the spelling. I think I have to check. Oh, this is just fun fact. If you want to read more about how this theory of sets was actually developed, right? Of what they did in the 18th century and how Cantor reached this place, was exactly the story that we did. We realized that there are countable sets. All of them have the same cardinality as natural numbers, and then there are uncountable sets. One question is, do all of them have the same cardinality as reals, which we will try to see now. And then also this question, right? Can there be sets between reals? Can there be a set that has cardinality larger than the cardinality of natural numbers and lesser than the cardinality of reals? At least in the picture, it is immediately not clear, right? Because if you look at this picture, if I initially posed you this question at the beginning of the lecture, beginning of the discussion, what you would have said is probably yes, because these are all strict supersets. So maybe they are all in between N and R. But now you know that all of these sets have the same cardinality. So they are in one bag. And then this set is another bag. So we don't know if there is anything in between. But this is just fun fact. This is not part of the lecture. Yeah, if you want to search more about it or read more about it, you can do that. Okay, so now let's get back to PFMD. So maybe I will give 5 minutes for you to think about a proof, try to mimic whatever we did for reals. One approach was what Razvi had suggested. But can you try a diagonalization data? Okay. Maybe you can take 2-3 minutes and then we will see the proof. But the question should be clear, right? So to demonstrate that it is uncountable, you have to demonstrate that if there is a function f that is bijective between capital N and P of n, or between naturals and the power set of naturals, then that function cannot be bijective. Okay, so I will give.
We list it out, and if we see if the ith element is there in the ith set you have listed, if it's not there, we include it. If it's there, we don't include it. And that should work.
And you will construct a set that does not have a pre.
And it's a different set from any of the set till now.
Yeah. Okay, but yeah, so others who haven't seen it also should digest it for some time. So what do we want to do? So if you are asked, you're given a set like the power set of naturals, and you want to show that it is uncountable. And I will give you one hint, and then you can start thinking about it. So if P of n is countable, then you know that there exists a function f between the set of natural numbers and the set of power set of natural numbers. I'm not sure if P is written like this, but still, that is a bijection. Right? So they both have the same cardinality. So on one side you have the set of natural numbers, on the other side you have all the subsets of natural numbers, and you give a one-to-one correspondence between these. I will use a different. So you have natural numbers 1, 2, 3, 4, 5, and so on. And here you have some sets. So I will just put some sets. The set of primes might be here. 11 is there. 9 is there. So 2, 3. And there is a one-to-one correspondence between these. That is to the set, to the natural number 1, you're going to associate 4, 5. The natural number 2, you're going to associate 1, 2, 3, and so on. So there is a way in which you can list or enumerate the set of all subsets, the power set.
Excuse me, ma'am. Is this a feasible alternative way to prove it? Like constructing a bijection between the power set. Oh, sorry. Did I interrupt?
No. Go ahead. Yeah.
No, like constructing a bijection between the power set of n and r, or at least actually like 0, 1.
So you want to construct
Yes, ma'am. Like if you like define a function from the power set to r, being like this, being like the sum of 10 to the power of minus x, where x belongs to s, where s is an element of the power set. Like
10 to the power minus x into x is the length of that integer. You can also say like the concurrent.
like I mean summing. Okay, yeah. Just as a.
Yeah. So I'm seeing this for the first time. So we will all try to either prove it or refute it. You can go ahead with that. Yeah, I'm fine with this discussion. So this is what you want to do, right? You for every set in the power set, you want to assign a real number in 0, which is defined this way.
Yes, ma'am. Yeah.
So S could be an infinite set. So what is this? What is the natural number? So if S is n itself, if it's a bijection, then for every set you need to come up with a natural, with a real number, right? In 0, 1.
Yes, ma'am.
So S could effectively be the set of natural numbers itself.
Yes, ma'am.
So what is a real number corresponding to it?
It's just 0.111111, like ad infinitum.
Okay. You look at the corresponding index. If it's there, yeah, okay. In that location, you're going to put 1 or something like that. Point followed by that.
Or actually, rather than 10 to the minus x, actually 2 to the minus x, and instead the binary representations for the numbers. I think that would be a lot better.
Yeah. So
Right.
that is exactly how one proves that the set of all binary strings of infinite length is uncountable. So from the binary strings, you are constructing reals. Now what you're doing is from P of n, you're constructing binary strings, from which you can construct reals. This will all boil down to showing understanding that reals are uncountable. That is it. So as an exercise, yes, but you have to formally prove that this is a bijection.
Okay, ma'am.
So generally, one thing is that this is a tip. Okay, this might not work. Like you might all be really cool and you'll be able to construct bijections. But in general, if you're given a set and asked to construct a bijection to natural numbers, it can be very tricky. So for one example is this. Did any of you attempt to construct the actual function here, explicit function for rationals? It can be actually messy. Like you have to look at this particular diagonal and see which are all not reduced forms. Only for those you have to give the numbers. All reduced forms you should not give numbers. Right? So if I asked you to explicitly write down the bijection, it can be very tricky. I'm not saying that you cannot do it, but in general, coming up with the bijection, or even this case, right? This function, it's easy to show that something is an injection. But to show that some function is bijective can be really hard. Right? You should ensure that everything has a pre-image. Yeah, but it is true. I'm not disproving this argument. I'm just saying that, yeah, this doesn't work. Diagonalization is the best thing you should try. I think I can erase this. Are there any questions about the point that he raised? Yeah, if you can formally prove that it is a bijection between P of n and the interval 0, 1, then it is fine. Okay, so this function, let's call this f. Okay. Suppose the set is countable, then this function should be a bijection. Right? So we assume that P of n is countable. So we know that there exists an f that is a bijection. So f is a bijection. So this means that for any subset A that you pick here is that is in the power set, for any A in P of n, you know that there will exist a natural number. Let's call this number B. B here, that corresponds such that B in n, such that f of B is A. Is it clear? Okay, so now can someone try to construct a set that might not have a pre-image? So what do we want to show? We want to show it is uncountable. So now I've assumed that it's countable, and I know that there exists a function. So corresponding to any set, I know that there is a pre-image. Okay. So let's call this set SB. For every set, there is a corresponding. Now, what I want you to do is exhibit a set that will not have a pre-image. If that is the case, then what have you proved? If you assume that there is a bijection, then that function can never be surjective. Right? You can always find a set in the power set that does not have a pre-image. So no surjective function exists from the power set of natural numbers to set of natural numbers. That is what we are trying to do. So maybe you can take some time. One of them actually answered it earlier, but just to digest. If you're seeing this for the first time, you can take some to construct a set. So what I want you to do is construct a set that cannot have a pre-image. Just to match my notes, I put A. Okay.
So we can do something.
Mhm.
So since capital N has a pre-image and it's just a single element, we can just not consider capital N for the moment.
Mhm.
And every other subset of N will have at least one element that of N that is not present in that. Okay.
Okay.
And for each set, from each of these subsets, we take such an element such that it is not present in that.
In the image, right?
And that subset is nowhere in the counting, I think. Like except N. So I'm not considering capital N for the moment.
Okay. So whatever he said is something you have to formalize. If I think, right, you have to write it down. Formally. But does everybody get what the idea could be? So what do you know? You know that for any set which is a subset of natural numbers, from our assumption, you know that there exists a natural number that is its pre-image, right? So let's just look at one element here. So let's look at an element. Because this is a bijection, this also maps to some set here. I'm just formalizing what all of you said in different languages. That is all. So this set SP is in the power set. And he exactly what he said was that you have to figure out whether, so this is a subset of naturals. So it could contain B or it may not contain B. There are only two possibilities. So I'm just going to call this element B selfish if it maps to a set that contains itself. So for any B, you look at for all B, for any. So for any B, we say that B in N, we say that B is selfish. If you look at f of B, and that is SP, and that set SP contains B. It's so selfish that under the map, it puts itself in the set SP. Right? For example, here 2 is selfish. And 4 is not. I'm just using some terms. It's not necessary that you have to write all this. It's exactly whatever the intuition you all probably have. Right? You have to just construct a set that is not in this list. That is all. All right. Okay. So now, if you look at the left-hand side of the set of natural numbers, some elements are selfish, some of them are not. Under this map, F. So there are some selfish elements and some non-selfish elements. You look at the set of non-selfish elements. Right? That is, these are all elements. If you look at the corresponding sets, the same number won't be in that set. Right? So this thing that he said, right, we are not considering capital N, it's not necessary to consider capital N. You just have to demonstrate one set for which there is no pre-image. That's a pre-thought thing. So you look at all the non-selfish elements. So it's all those A in natural numbers such that A is not in SA. So we know that A is a subset of natural numbers. So what can you say? On the right hand side, you have all subsets of natural numbers. So this A must also appear somewhere. Okay? So we know that A appears. So A is in and A appears somewhere. So if you've already understood the argument, this is just to show you how to write it. A appears somewhere in the RHS. And because F is a bijection, you know that there is a natural number that is associated with this set A. Right? Let that natural number be M. So M be F inverse. So now you know that A is the set of non-selfish elements. And you don't know whether M is selfish or non-selfish. It could either be selfish or not. Those are the only two cases. So either M is in A or M is not M. These are the only cases. Suppose M is in. Then can someone say what is going on?
M can't be in the set, and if like M is in the set, then M can't be in the set. And if M isn't in the set, then it has to be in the set.
Yeah. So you all see the issue, right? So if M is in the set A, you know that M is selfish, right? That's how we define selfish sets, selfish elements. Right? M is selfish. But A is the set of non-selfish elements. So this is not possible. So M in A is not possible. So M is not in A is not possible. Okay. But if M is not in A, right, then we know that M is non-selfish. When we say selfish or not selfish, this is with respect to the bijection F. Under F, M does not map to a set that contains M itself. M is non-selfish.
Hello, ma'am.
Uh-huh.
Ma'am, how do we know that the set A is non-empty?
Yeah, we will come to that. Yeah, so A could be non-empty. In this whole argument, I did not say, A could be empty in this whole argument. So far, we have not done that case. For these two statements that I'm saying, just assume that A is, yeah, we will come to that. So suppose M is not in A, then M is non-selfish. But then if this is the case, by definition, M should have been in. So both these things lead to a contradiction. So the only thing we have not done so far is A could be empty. But if A is empty, can someone say what is the problem?
Then
M wouldn't have a PH.
Yeah, right? Then empty set will not have a pre-image. Is that clear? So I don't know the name student who raised this question.
Yes, ma'am. I need to think a bit.
Okay, so suppose A is empty, right? Then what does it mean? It means that no no element is, so A is the set of non-selfish elements. If that is empty, okay, then it means that every element is selfish, right? So every element here in 1, 2 in the natural numbers, so every element of N maps to a set. Every element A maps to a set that contains A. Correct?
Yes, ma'am. Now I get it.
So then, what does the empty set map to? What is the pre-image of empty set?
Ma'am, if we assume that it has a pre-image in natural number, then we get a contradiction. As because all the subsets, I mean, all the elements would be selfish then. And if we assume that it has a pre-image B, then we are actually saying that the empty set contains B, which is a contradiction.
Yeah. So I'm just using, yeah, so whatever you said is right. I'm just using the same language as selfish so I can complete the proof. Okay, so is this clear? If there are any questions, we'll stop and take.
Ma'am, I have a doubt.
Uh-huh.
Suppose, let's assume the set, I mean, there are no selfish elements. So, sorry, there are no non-selfish elements, like every element is selfish.
So
in
A
that
is
case,
empty, right?
yeah, A is empty. So in that case, what if we include 0 into natural numbers and assign 0 to the empty set? So in that case, can we conclude that N union 0 has a bijection with P of N?
Okay, so what you want to do is, I don't know if I have to give these notes because I have to post it, but I think I'll try.
Ma'am, could you repeat? I was not able to hear you. What
No, I am just going to write whatever you said.
Oh, okay.
See, I'm also thinking because you're all giving lots of approaches, right? It's not like I have ready-made answers to everything. So, yeah, so what he's saying is the following. Okay. F of 0 is empty. Is this what you're trying to say?
Yeah, 0 is empty and 0 is assigned to empty and every element is selfish. So with this setting, that argument.
Okay, yeah. So what you have to now do is you have to show that n union 0 is countable. Yeah, for our definition of countability, we have actually said that it is countable if there exists a bijection from this to natural numbers, right? So yeah, this is something that I think I can say. Like if it is wrong, someone should put it. So what you are trying to show is n union 0 is countable, right?
No, I'm trying to build a bijection between n union 0 and the power set of n.
Correct. That's what I'm saying. So what we have to do is, if we wanted this to work, we have to change the definition of countability is what I'm saying. So when is a set to be countable? If there is a bijection between n and its set. But now what you're demonstrating is that there is no bijection between n union 0 and power set, right?
Yes, ma'am.
Right. So it won't fit with the definition, but I don't know if you can change the definition as n union 0 being countable. Maybe that's okay, because even if you add 0 to the set of natural numbers, it will still be, it will have the same cardinality as n, because you can do the shifting that we did last time. Okay. But yeah, this is a bit strange, right? In the sense that, yeah, so countability usually, in the usual sense, it must have a bijection to n. It has the same cardinality as the set of natural numbers. So I don't know if you think about whole numbers as the left-hand side, then is it okay? Then yeah, you can still enumerate, so that is fine. Yeah. So maybe with this, you can construct another set. With this bijection, maybe you can show that.
One question: how did we conclude that the empty set has no pre-image?
In this argument, or what we?
Yes, in the argument that you gave.
Okay. Okay, I will just come back to that. Maybe I have to think about it. I have not thought about considering the whole set of whole numbers instead of natural numbers.
Yes.
I will think about it. Okay, yeah, I'm not entirely sure whether there is a definition. Yeah.
In the whole number case, if we assign 0 to 5, then we always have 0 which is non-self.
Which is? Sorry. You always have 0 that is? Hello?
Non-selfish.
Non-selfish.
Yeah, because like in P of n, you would also get zeros, right?
Yeah. So then, yeah, I think what he means is here there should be whole numbers and P of whole numbers. So 0 will be in all the sets. So I think you can still construct a set that has this. That is what my feeling is. Is that what you're trying to say?
Yes, ma'am.
Yeah, so I think, so I don't know the name of the student who asked this question.
I was the one.
Ajay Krishna. Okay, Ajay. Yeah, so what she says is, if you were going to demonstrate a bijection with the left-hand side as 0, right? Then even in the right-hand side, you must consider subsets that have 0. Right? Otherwise, one side is the set of natural number, power set of natural numbers, and the other side is whole numbers.
No, what I was actually trying to say was, since we are not able to build a bijection between natural numbers and the power set of n, let's try to build a bijection between whole numbers and power set of n, so that since whole numbers is countable, power set of n will also be countable. Whole set is countable because there exists a map such that you just increment it by 1 and there exists a map. So that's what I was trying to say.
So I think his idea is you have W and you have P of n. You try to construct a bijection between W and P of n and try to come up with a contradiction, because W is countable. This is not a bijection. That is what you're trying to say, right? Mimic the whole, everything else will remain the same.
Yeah, yes, ma'am.
Yeah, at the moment, I haven't seen an argument where the definition of countability itself is thought in terms of whole numbers. Yeah. Maybe, yeah, but you have to ensure that the set of whole numbers is counted.
Yes.
It might be fine. Yeah, but somebody else had a question, so I will just answer that and come back. Because that
Yes,
is about
ma'am.
something that I did.
Ma'am, I'm confused why we need to consider the case of A being empty separately. Because can't we just say that if A is empty, then M is not in it? Because we can still consider that some natural still maps to an empty set.
Okay, so I didn't get what you said. Maybe can you just say it a bit slowly?
I'm asking why do we need to consider the case that A is empty separately? Like after we
After the
show the
proof here only. Okay, so
yes,
do you
there.
think that it's already covered here?
Yes, ma'am, I don't see. Yeah,
Okay.
I don't see where we are taking that A is non-empty.
So if A is empty, then it would be that yeah. So this M is in A will not occur. You know that every element is non-selfish, right? So it's here. There is no element is in A, and that is exactly what it is. Then what is the natural number corresponding to the empty set? There is none, because every element is non-selfish. It is actually covered here. Is that what you're also trying to say?
Yes, ma'am, I think so.
Ma'am,
So
so in the second case, we assume that M does not belong to A, and then we conclude that M is non-selfish, and then we conclude that M belongs to A. So that is a contradiction.
Correct. But what he's saying is we did not assume, we did not need A being non-empty, right? In this case. In the first case, yes. In this case, we do need A is non-empty. That's why there is some M in it. So you can think about the whole argument as either A being non-empty or A being empty. If A is non-empty, then I know that there is an element in it, which means it's selfish, but then A is the set of non-selfish elements. So that is not possible. So what he is trying to say is A is empty is already covered here. There's no need to bring about a separate discussion about it. I think that's what he was trying to say.
yes, ma'am, that's I think.
Yeah. So I wrote this because somebody had actually asked what happens to the empty set. So whatever is written here is whatever happens in this case. I just substituted A equal to empty set. So up until this, we did not. It is not necessary that we assume that it is not empty. For this case, yes, we did assume that it is not empty.
Ma'am, so in the question about the constructing a bijection from whole numbers to power set of n, so we can assume that there exists a bijection from whole numbers to power set of n, and then we can also construct then we can construct a bijection from whole numbers to natural numbers. Then there will be a whole bijection from natural numbers to power set of n, but we have proved that there is no bijection from natural numbers to power set of n.
Right. That is exactly what even he said. What the others also suggested. So you put zero. You put zero here. It's fine. But what you have to show is that even if you add zero to the set of natural numbers, it is still countable. This we did last time. So we have to use that to say that the set of whole numbers is countable. That is what I said.
Okay.
It's exactly right what you said. So when you just talk about whole numbers, it is not clear whether whole numbers are countable or not. Right? So that is one thing. That is exactly what you pointed out. Yeah, that is true. That is right. I hope like Ajay is convinced that it is right.
Yes.
Ma'am, once more, could you please say how empty set does not have a pre-image?
Okay, so let me just erase all the snubby work I did. So now let us look at, okay, suppose the set A is empty, right? What does it mean? It means that there is no non-selfish element, right? So A is the set of non-selfish elements, and you know that A is empty. So what does it mean? It means that every element is selfish. So if you look at any element A on the left-hand side, it will always map to a set that contains A, right? From I'm looking at the left-hand side being 1 to 2, 1 to 2, all set of all natural numbers. So 1 always maps to a set that contains 1, 2 always maps to a set that contains 2, and so on. If that is the case, then what can we say about the empty set? It will not have a pre-image, right?
Yes,
because you know that every element maps to a set that only contains each set, and it can contain some other elements. Right? So empty set cannot have any pre-image. Okay. So after the long discussion, I hope that you are convinced that the power set of natural numbers is uncountable. Okay, so what are countable sets? We have Z, Q. Here. Okay, I'm not writing N because N by definitions. In uncountable sets, we have R, we have power set. So one exercise is, so we do know that all countable sets have the same cardinality as the set of natural numbers. Another exercise, which actually you all solved here, but I'm still going to do it. What can you say about the cardinality of this versus the cardinality? Some of you did construct a bijection, but try to write it down. Are these two the same or not? Okay. So now if you know N, you know that P of N has cardinality strict. So now to show that is, so what have we shown? We have shown that the set of naturals, which is a subset of power set of N. So this is a corollary of whatever we shown. So we know that N is a subset of P of N. So we do know that the cardinality of naturals is less than the cardinality of this. And we know that P of N is uncountable. So what we have shown is, in essence, the power set of natural numbers has strictly larger cardinality than the set of natural numbers. That is what we have shown. So this is exactly what it is the case for finite sets also. The same is true for natural numbers. So if I first asked you this question in the beginning of the lecture, it might have been slightly unclear. Because for finite sets, everything seems natural. You can just count. This is N and this is 2P. But for infinite sets, you could not say that both the sets are infinite. So how do you compare the cardinalities of N and the power set of N? Here is a proof that tells you that the power set of naturals has strictly larger cardinality than the set of naturals. So now one can also think about this. N, P of N, P of N, and so on. Keep doing this. Right? What kinds of sets do you get and what are their cardinalities? But this is a quick picking, like the continuum hypothesis. This is not part of the course. If you want to think about it, you can. So I'm not including the notes.
The continuum hypothesis says that there is no set of cardinality strictly between the set of cardinality of the uncountable rational numbers and the countable
reals.
The countable natural numbers, right?
Right.
So is it true that if we have a set X, which is whatever naturally more than uncountable, so if we have a set capital X and we assign cardinality to it, and there is no set such that whose cardinality is between cardinality of X and cardinality of power set of X. Is that true?
It is the same as. So he's asking: is there a set between S and between that has cardinality between S
and power set of S? Yes, for any arbitrary set S. For S equal to natural number, this is the continuum hypothesis, but is it true in general?
So if S is countable, then this is the same as N, and if P of S, yeah, I think this will be the same as continuum hypothesis. This should be. If S is any countable set, then you can go via N, P of N to P of S. If S is finite, then it's a different story. There's nothing there.
Yeah, for finite. But what if S is bigger than R, the reals, or more than LF1?
Yes, then the power set of this, so that will be similar to this, right? So what can you say about the cardinality of, so we know that this is true. And
yes,
you are saying that this is there. And I think this is what is saying. Yeah, so this will require some more detail about continuum hypothesis. So in general, if you ask the answer to continuum hypothesis, it can either be true or false, but I have to give you a lot of details about that to answer more things about the continuum hypothesis. I have a feeling that if there is a set S that is between N and P of S, then you can also find another set between N and P of S. which will answer the continuum hypothesis. Yeah, I don't want to talk about the answer to the continuum hypothesis because I have to describe what is called the Zermelo-Fraenkel set theory. I don't want to get into it. Yeah, this might have something to do with the continuum hypothesis. You have to look into it. But that was just a fun fact for you to look at. We won't discuss the continuum hypothesis beyond this. There is something like that, and it's good to know. Probably real analysis when we will discuss more. Okay, so I have some more time. I have a lot of things to do. Okay. So maybe I will put 3 questions and then we'll see where it is. Right? So some properties of countable sets. You may or may not have tried this already. So one is that any subset of a countable set is countable. The second is Cartesian product. Is countable. The third is countable union of countable sets. Okay, so yeah, these 3 things you can think about. If you solve it, great, but we will also try to solve it in the next lecture if you don't. If all of you are able to solve it, then we just do it. So some questions that we want to see later on. What can we say about the cardinality of 0, 1 versus the cardinality of 0, 1? We hope the notation is correct. So these are some questions that we think about. We will solve all of this, but yeah, I'm just trying to show. Whether do you believe that both these sets have the same cardinality? So yeah, these things you can think about. But now I want to do something probably simple so that I can finish in 5 minutes. So one thing is, let's try to solve this statement here. This is something similar to what one of the students had posted, right? In between example, right? What if we have an injective map? For example, if you look at n cross n to n, right? What was the map that we defined? We look at mn, move to the n, 3 to the n. It's very easy to show that this map is injective. There is no work to do, literally. But can you try to figure out if this map is surjective or not?
It's not surjective.
Okay, so this let me write it. So F is not surjective. Do you see why that is the case?
Any number not divisible by 6 won't be there.
Sorry, I did not hear the last.
Any number not divisible by 6 will not be there.
Right. So yeah, so there is no equivalence. It's not divisible by 6.
Yeah, the other one.
So this map was very easy to produce, and it was a most natural.
There can be 2 comma. Sorry. I thought 0 was also there.
Yeah, 0 is not there. But there could be other maps that are injective and surjective. Maybe you should put in 5 also and raise 5 to a certain power, and we can try to do this. We can somehow get around this trying to fit in three images for numbers that are that 6 does not. That is possible. But at least this map was very easy to create, and this was the most natural map. But unfortunately, it was not bijective. So this you could not use directly to show that n cross n is the Cartesian product of n with itself is countable. So now one might ask, okay, so what if I have an injective map? Can I somehow massage it to get a surjective map? If I could do that, I can do that here. Okay? So that is the next question. So let us say that there exists an injective map, okay, from S to N. Okay. Then can there be a surjective map from N to S? Surjective function G. This is not very difficult to state. Let's just try to do it. I'm sure you all already know how to do it. So F P from S to N is injective. So if you look at it, there is S. So it is 1 to 1. The only problem is that there could be several elements that do not have a pre-image here, like similar to the map that we have here. So if that is the case, then someone try to define a G from capital N to S. So what you have to do is essentially assign 3 images for this, right?
If an element is in the range, then it goes to pre-image, otherwise it goes to 1.
So just pick some element, that's what we're saying. So for all these elements, I think what we're saying is this. For all these elements, pick one element here and put them there. Is that what you're saying? Similarly?
Yes, yes.
Right? You chose one instead. Right? So what you do,
Yes.
the most natural, right? This portion we don't know, I mean, these things we know don't have images. Assign a grey image to each of them. We don't care about what it is. So G of n is, if it is already defined by f, right? Let it go there. So S, if f of s is equal to n for some SMS. Otherwise, you just assign it to some element here. So what do we know? We know that G is surjective. Right? If you look at any element, it definitely has a pre. So if there is an injective map, then we can always construct a surjective map. But now the question is, if you have an injective map, you have a surjective map. But to show that some set is countable, right? For example, n cross n, you have to show that there is a bijective map between S and N. So let S be any set. What do you have to do to show that it's countable? You have to demonstrate a bijective map between S and N. So now this is the question that remains. If we have an injective map and a surjective map, two different maps. Remember, what you want is one map that is both injective and surjective. But unfortunately, you're not able to do this. You have one map that is injective, one map that is surjective. Can you construct a map that is bijective? It seems unclear at the moment because G is not an inverse of it. Right? Otherwise, you could probably do some massage and do it. You can try to compose. But whatever you do, one of them is, so it can very well, so it is clear that G is not injective. Right? It is definitely many to one. And the F that you started with is not subjective. If it is subjective, then you directly have a subjective. So if you have an injective map that is not subjective, then you can always come up with a subjective map. That's what this is. So now the question is, if there is a map F from S to, or in general, let's say A to B. A, where all sets are infinite. And a map G from B to A. That is subjective. And one construct a map H from A to B, that is bijective. So suppose the answer to this question is yes, then this itself is enough, right, to show that n cross n is countable. There is an injective function. From that, you can construct a subjective function. You can massage these two to get the bijective function. So then your life becomes a lot easier. You don't have to do any of this circus that we did earlier to show that some sets were countable. Right? For all of this, it's always easier to get injective maps. Okay, so this is
this doesn't seem true. Were we claiming this is true?
Why
I
do you
think
think that this is something?
in the question, I think both of them should be injective, or maybe the ordering should be opposite.
A to B, like B to A should also be injective, or A to B should be surjective.
Yeah, exactly.
Otherwise, we can just find a injective map from N to R, and then again surjective map from R to N, and then we
Okay,
can.
subjective, and also you mean that yeah, one. So maybe this is A to B. I think that's the easiest way to change. Right. I think that's the easiest change to make. Okay, yeah. So the answer to this question we will see next lecture. But before that, we'll also do a few more things. Some things that I did not do this time, especially this one.
Ma'am,
Huh.
in the last theorem, like if we have an injective map, can all this be avoided just by saying that since n is countable, all its subsets are also countable, right?
Yes.
So we already have a map from whatever set we need to a subset of n, which is countable.
Right.
And
So
from
that's
that,
it.
yeah.
You have a bijection, right?
Yes.
Yes. So what she's saying is, yeah. So what I wanted to say at the end of it is that it is enough to prove an injective map to show that a set is countable. It is enough to come up with an injective map from that set to a subset of n. I think that is what she's also saying. Yeah. So maybe we will do this first. But yeah. So how did you all try to? Maybe I should stop. So this thing, right? I'm not sure if you have attempted this. Any subset of a countable set is countable. If you haven't, it's a nice exercise to do. Yeah, let me know how you did it. How you were able to show it next time. Try to show that the subset of a countable set is countable without using any principles that you have not seen in this class. I would have actually wanted to do one or two more things, but it is fine. I will just stop here if there are no